Okay, so this is going to be the recitation for our chapter 18, which is our aqueous ionic equilibrium, including buffers, Kas for buffered systems, pHs, KSPs, etc. So we're going to just do 5 problems that are pretty good representations of some of the different problem-solving techniques that we should be looking at. And we'll talk about the rationale as we go through. So the first problem here is calculate the pH of a buffer that is 0.225 moles per liter, or molar, acetic acid, which is our HC2H3O2, and 0.162 molar potassium acetate. So right out the gate, when we're looking at this, we see we have a weak acid with our acetic acid, and we have a salt of the conjugate base of that weak acid with our acetate. And we are given a Ka for acetic acid, which is 1.8 times 10 to the minus fifth. So the question is, how do we calculate pH of this buffering system? So right out the gate, what we know is we have a concentration of our weak acid. We have a concentration for our conjugate base. So we know concentrations for our weak acid conjugate base pair. This is looking like a good setup for a Henderson Hasselbach style problem. We also have the Ka. Now, Henderson Hasselbach is pH equals pKa plus the log of the concentration of the conjugate base over the concentration of our weak acid. So we don't have the pKa, but we have the Ka, which is nearly as good. Because remember, pKa equals the negative log of Ka. So I think this is everything that we need to solve this problem. Let's do Ka first, so we can just sub in here. This will say pKa for the acetic acid equals the negative log of the Ka, which is 1.8 times 10 to the minus fifth. And we can easily do the solution, and it's 4.74, which is our pKa for acetic acid. Now, what we can do is we can literally plug and chug. We don't even have to rearrange, because pH for this is going to equal our pKa for our weak acid plus the log of the ratio of our concentration of our conjugate base, which is 0.162 moles per liter, over the concentration of our acid, 0.225 moles per liter. And if we do this solution, it's going to look like, let's see, 4.74 plus negative 0.14 equals 4.6. And that should be our pH for this buffered solution of weak acid, acetic acid to acetate. Now, you can do a mental check on this as well, and I recommend that. So does this make sense? Well, we have more of the acid in the base, so it's going to be a slightly more acidic. This makes sense. This is a reasonable answer. Nothing too wild here. So let's move on to something a little bit more complicated. Scrolling to problem number 2. So let's calculate the pH of a solution formed when you mix 500.0 milliliters of a 0.15 molar ammonium chloride solution with 200.0 milliliters of 0.20 molar ammonia. So we're going to see another buffer here, because we know that ammonia is a weak base and ammonium is its conjugate acid, or vice versa. And the Kb for the ammonia is 1.8 times 10 to the minus fifth. So this one's going to be a little bit more involved, because we don't have a final concentration of the buffered solution. You're mixing these two solutions together. So one of the cruxes of this problem is you have to realize that when you have 500 mils of something and you mix it with 200 mils of something else, the final volume is going to be 700.0 milliliters. And that's going to change the concentrations of both of the components. So the best way to do this is to just find the number of moles of everything in solution and then divide by the final volume of that solution to determine the new concentration in moles per liter of the components of this buffered mixture. So let's go ahead and do that. Let's start with, we've got the ammonium chloride. So we've got 0.15 moles per liter of the ammonium chloride, and we've got 0.5000 liters. I'm just going to do the mental math, moving 3 decimal places from milliliters to liters. We've been doing this for a while, so liters is going to cancel out, and that means we're going to have 0.075, sorry for the ugly 5, my tablet powers are not leveled up yet, moles of ammonium chloride. We also have a 0.20 moles per liter of ammonia, and we have 0.2000 liters of ammonia. So this means that we're going to have 0.04 moles of ammonia. What we can do now is we can divide each of these by 0.7 liters, because 500 mils plus 200 mils gives us a final solution volume of 700 mils. So I'm going to go 0.7 liters for both of these. I know, I apologize for my tablet writing, it's really atrocious, but hopefully everyone can follow. And this means our final concentration of each of these is going to be 0.107 moles per liter of ammonium chloride and 0.057 moles per liter for ammonia. So now we've got our final concentrations of both the buffering components that we're interested in. And what we can do now is see what equation we're interested in. We're probably going to be using Henderson Hasselbach again, which is pH equals pKa plus the log of the conjugate base over the concentration of the weak acid. Now, what we don't have is a pKa. What we're given here is AKB. So what are we going to do about that? Well, if Kb for ammonia is 1.8 times 10 to the minus fifth, what we can do is just find pKa from that, because pKb equals negative log of Kb. So if we just substitute in negative log of 1.8 times 10 to the minus fifth, that's going to give us a pKb of 4.74. If the pKb is 4.74, all we have to do is remember that pH plus pKb of any aqueous buffered solution is going to be 14, right? So what we can just do is say pKa is going to equal 14 minus pKb, and that's going to give us 9.25-ish, maybe 9.26 if we were to, round correctly. But this is going to be close enough for, well, let's round correctly. Let me just, because 2.55, so let me call it 9.26. So now we have everything we need. We've got a pKa, we've got concentrations of everything that's relevant. So pH equals pKa plus log concentration of our conjugate base over the concentration of our weak acid. pKa is 9.26 plus log concentration of our conjugate base, in this particular case, is ammonia, because the weak acid is ammonium ion, so that's going to be 0.057 moles per liter. And the concentration of our weak acid is 0.10 0.07. I'll give you little dashes for the sevens, and that means 9.26 minus 0.27 should be 8.98 or 8.99, depending on how you're rounding, but this will get you close enough. And I'm not going to be super critical of sig figs or anything in this, obviously, because it's multiple choice. Let's see. So that was a good one. Let's see what we've got next. Let's scroll down a little bit. Ooh. Okay. So next one, we've got this 1.00 liter buffered solution, which is made up of 0.250 moles per liter of hydrofluoric acid and 0.250 moles per liter sodium fluoride. Remembering, sodium fluoride in solution will be sodium cations and fluoride anions, with the fluoride anion being the weak or the conjugate base to the weak acid, hydrofluoric acid. So what we're supposed to be doing here is calculating the pH of the solution after the addition of 100 milliliters of 1 molar hydrochloric acid. The Ka is given for hydrofluoric acid at 3.5 times 10 to the minus fourth. Okay, this one's not too bad. It's nice because we're given the concentrations of both of the buffering components in the solution. We don't have to determine that like we did in the previous problem. But what we will have to do is look at what's going on with the reaction. So just as a summary, what we're going to see here is we have a solution made up of hydrofluoric acid and fluoride. And when we add the hydrochloric acid to this, that strong acid is going to react preferably with the conjugate base. And it's going to convert that fluoride to hydrofluoric acid. So it's going to be consuming your fluoride and making hydrofluoric acid as part of consuming the buffer. So we'll just keep that in mind as we start working through this problem. So the first thing we really need to do is calculate the number of actual moles of hydrofluoric acid and the number of moles of fluoride. And then we're going to calculate the number of moles of free protons from the hydrochloric acid. We're going to use the amount of moles of hydrochloric acid to determine how much hydrofluoric is made, how much fluoride is consumed, and then we're going to plug in those new values into the Henderson Hasselbach equation, and that will get us where we need to go. So that's going to be our strategy. Let's see how it works out. We've got 0.250 moles per liter of hydrofluoric acid, and we've got 1 liter. So liters are going to cancel, and that means that we have 0.250 moles of hydrofluoric acid in this solution. We also have 0.250 moles per liter sodium fluoride, which means we have 0.25 moles per liter sodium cations and 0.250 moles per liter fluoride anions, because they're separate. We've got 1 liter. Liters are going to cancel, and so we also have 0.250 moles, and I'm just for ease of tracking, say, of fluoride in solution. Just make it clear that that's our conjugate base. If you want to draw it as sodium fluoride, that would be fine too. And then we need to figure out how much hydrochloric acid we have. So we've got 1 concentration of 1 moles per liter HCl, hydrochloric acid, and we've got 0.100 liters, since we have 100 milliliters. I'm going to get those liters to cancel out, and that means we're going to have 0.100 moles of hydrochloric acid, or you could think of this as 0.100 moles of free protons. So now you can see what's going to happen. When we add, we initially have this much, right, initial. And you can make an ice table, but if you've been doing ice tables for a while, you're probably starting to do this in your head. And since we don't have any x values we need to solve for, this is pretty straightforward. I'm going to say that in this reaction, the hydrochloric acid, all of it, 0.1 moles of hydrochloric acid, will react with the fluoride, and that means it's going to consume 0.1 moles of fluoride, and it's going to produce 0.1 moles of hydrofluoric acid. So after the reaction, we're going to have 0.350 moles of hydrofluoric acid, and we're going to have 0.150 moles of fluoride. And these are going to be our final number of moles. And then all we have to do is plug these bad boys into our Henderson Hasselbach equation. Or can we? Oh, we do, because we have Ka. So we've got Ka, so we need pKa. So once again, pKa equals negative log of Ka, so negative log of 3.5 times 10 to the minus 4 is going to give us a pKa of 3.46. Whew. All right. And so now, as a mental check, whatever our answer is, remember we're adding acid to this buffered solution. So even though it's going to resist the change in pH, it's still going to affect the pH. And if we're adding acid to the solution, in the end, we're going to make it slightly more acidic. We expect the pH to drop from a 50 from the initial, start point. So that said, I would expect adding acid to the solution to see a pH that indicates addition of acid. So let's see here. Well, let's say pH equals pKa plus log of our conjugate base over our weak acid, and we'll call that 3.46 plus the log of, what's our conjugate base? Fluoride. So concentration of fluoride at final is going to be 0.150. Concentration of hydrofluoric acid, our weak acid, 0.350. And if we solve this, we should get 3.09 for our final pH, following the addition of the 100 milliliters of hydrochloric acid. Some of you are probably astute and you said, hey, Dr. McGill, that's not concentration, that's the number of moles. And you'd be right. If you wanted to, you could take these numbers of moles and you could then divide by the final volume of 1.10 liters, and both of these values would change by the same ratio. But because this is a ratio we're taking the log of, it won't affect the outcome. So if you're not sure whether or not it would affect the outcome, it's safer always to find the concentration, which would mean taking those number of moles and dividing each of them by 1.10 liters, because remember, we started with a liter and then we added 100 milliliters to it. All that said and done, though, in this example, it won't matter because it happened identically to both, and because we're just looking at ratios, it will not change the final ratio in the end. It's still going to have the same pH value of 3.09. Let's see here. Uh-oh. There we go. Yeah, that's faster than scrolling, except I overshot. Let's see what we have here. Ooh. Okay, so this one's a little tricky, because it makes you think you're doing something and then you realize you're doing something else, and then you have to change gears a little bit. So this has got 100.0 milliliter sample of 0.10 molar ammonia. and you're going to titrate it with 0.10 molar nitric acid. The question, though, however, is determine the pH of the solution before the addition of any nitric acid, and gives you Kb for ammonia of 1.8 times 10 to the minus fifth. Now, oddball question, right? But let's sort it out. Important thing here. This is all a question about what's the pH of solution before any acid's added. So we're going to just say, forget about anything to do with titration. What's the pH of a 100 milliliter sample of 0.10 molar ammonia, given Kb is 1.8 times 10 to the minus fifth? That's the actual question here. And there's actually quite a few ways you could approach this, and I'm just going to do one of them. So, given a Kb, let's just do a simple ice table, and that'll get us where we need to go. So, remember that for the reaction of ammonia in water is going to react with the water, forming ammonium and hydroxide. And remember that Kb, I'm just going to draw this over here, is going to be an expression of concentration of hydroxide. So let's see here. Oh, also remember that in your ice table, water is a liquid, and therefore we are not going to be paying attention to that particular value. So let's say initially, what are our concentrations we have available here? Well, initially, our concentration is 0.10 moles per liter. We're not going to pay attention to water. I'm going to get rid of this Kb here because it's in the way of my table. And something to do with this equilibrium is going to start at 0 and 0. And so our change in the system, these are all 1 to 1 to 1 ratios. So we're going to lose X amount of concentration and gain X amount of concentration for both of our products. So our final is going to be 0.10 minus X, X, and X. And you're thinking, oh man, this looks bad, but we're going to use the approximation, and the minus X is going to be relatively insignificant because it's a weak base compared to our starting concentration of 0.10. So let's just put an expression together for Kb. So remember that Kb is going to be products over reactants with specifically our hydroxide. So we're going to have our concentration of ammonium. Wow, these are really, let me just start that over. That's just, I know, Bob, you know, they say that just happy little mistakes, but those are not happy mistakes. Those are terrible mistakes. There we go. Now we've got our products, including our hydroxide, over our reactant ammonia. And we know what Kb is. It's 1.8 times 10 to the minus fifth. And so what we can do is just substitute this in. Let's just sub in x's. I'll just call that x squared. You guys, you know, because ammonium is x, hydroxide is x, so I'll just call it x squared. And our concentration of ammonia is 0.1 minus x. That's going to equal 1.8 times 10 to the minus fifth. We're going to make this super simple by just approximating x to be very small so that the difference between 0.10 minus x and just 0.1 is insignificant in terms of the number of significant figures. And considering we only have 2 significant figures in our KB, that's not going to be hard to do. So I'm going to just get rid of it like that so you can see it. I know they're not tracking the process visually, but hopefully as we do this progressively, it works out. And then it's just a matter of solving for x. So multiply both sides by 0.1 to get x squared. (1.8 times 10 to the minus 6th now. And I'm just going to take the square root of both sides. And x should be, let's see here if I can write down this low on the tablet. 0, 0, 1, 3, 4. So, what does that value mean? That is the concentration of hydroxide and the concentration of ammonium. So, if you have the concentration of hydroxide, you can find POH. Because POH, just like pH, is the negative log of your concentration of hydroxide. So, if you sub in concentration of hydroxide, negative log of it, that should be 2.87, which means, remember POH plus pH equals 14, pH is going to be 14 minus 2.87, so pH should be 11.13. That's not terrible. The hardest part was changing gears. Because originally I was reading this thinking, oh wow, we're going to do titration, so right out the gate we need a number of moles of ammonia, then we need a number of moles of titrant, and then we're going to do it before and after, and then we're going to, no. Really, the question was, knowing the pKb of something, find its pH. Not too bad. Also note, the volume didn't matter, right? Why didn't the volume matter? Because the pH of solution doesn't matter on volume. If you have a 0.1 molar solution of ammonia, you're not doing anything to it. It doesn't matter if there's 1 mil, 20 mils, 50 mils, and 50 million mils. It's the same concentration of ammonia, and the pH is going to be the same regardless. So, slick. Let me scroll. I like the scrolling, like the drama scrolling. Final one. Determine the molar solubility of lead sulfate in pure water, knowing that the KSP of lead sulfate is 1.82 times 10 to the minus 8th. Okay, well, that's going to be a really slick one. So just remember what KSP is. KSP is just an equilibrium expression of products over reactants. The difference is that in this case, the reactant's a solid, so it's not part of the equilibrium. So it's really common for KSP to just be the products. So let's take a look at that. Remember, we've got our lead sulfate, solid, and in solution, it's going to partially dissociate into aqueous lead and aqueous sulfate. So the KSP expression for this solubility product is going to be the concentration of lead cations times the concentration of sulfate. And we exclude anything to do with liquid water because it's liquid, and we exclude the lead sulfate precipitate or solid because it's a solid. So there's nothing in the denominator. And this is going to equal 1.82 times 10 to the minus 8th. So here's the money question. What is molar solubility? So molar solubility is just the number of moles of solute that can be dissolved per liter to reach saturation. So at a saturated solution, how many, or another question, how many moles of a solute does it require to be dissolved in a liter of solvent, in this case pure water, for it to be fully saturated? Well, at equilibrium, which we're looking at right here, that's going to define our saturation point. So whatever our concentration is going to, let's see, the number of moles of solute that can be dissolved. And this is going to define exactly how much is dissolved. So all we have to do is solve for x, basically, because this is 1 to 1 to 1, right? So we can just say x squared equals 1.82 times 10 to the minus 8th. I'm going to take the square root of both sides. X is going to equal 0.000135. And that's going to be your concentration of these in moles per liter by definition. And that's the amount of this that needs to dissolve into solution. So you could also write this, I guess, as 1.35 times 10 to the minus 4 moles per liter. I mean, either or is fine. So yeah, that's going to be it for this review. And I hope that's, just give you guys a couple more examples of how to work through a problem. Hopefully the auditory component, the rationale as we work through helps. So that'll be it. Make sure you focus on these problems and similar problems to these. Make sure you include as much homework as you can get, honestly. And best of luck on the exam in the next couple days.